Hi friends, today we are going to discuss how the Bernoulli's principle is applied to a system which is under rotation. For example, suppose there is a cylindrical vessel. In the cylindrical vessel, we pour some liquid and then we allow the vessel to rotate about an axis with a constant angular velocity omega. As the liquid rotates, it will create a vortex, that is, there will be a depression at the center. This can be very easily seen if you fill your wash basin with water and by plugging in the hole and then just taking out your thumb, you will see that as the water flows down, it will come in the form of a vortex. So, when this particular cylinder is rotated, what we will observe is that the shape of the liquid will become like this. We are interested in finding the expression for height of this paraboloid shape in terms of angular velocity omega. Let us take the radius of this cylindrical vessel as r. First, let us consider the Bernoulli's equation in its regular form. If we apply the Bernoulli's principle as it is in the regular form, we will get an extremely contradictory result, and that is why it is necessary to modify Bernoulli's equation when we are applying it to rotational motion. In rotational motion, we are going to make a very important assumption that the entire fluid, as it rotates as a rigid body, and that is why we can apply the equation of circular motion, that is V is equal to R omega. If we apply this equation V is equal to R omega, you will realize that as the distance of the point from the center increases, say R1, R2, R3, the value of velocity also increases. So a velocity at this point and velocity at this point, if we consider, then V2 will be more than V1. Now let us first see Bernoulli's equation in its original format, and then we will understand how it creates a lot of confusion when we apply the same Bernoulli's equation to rotational motion, when the fluid is rotating. So let us first write the Bernoulli's equation in its original form, which says that the pressure energy plus half rho v square, where v is the velocity, plus h rho g should remain constant. Now, there is no confusion about the term of potential energy h rho g. As the height changes, h rho g is a perfectly valid term. But if we apply Bernoulli's principle to rotational motion, a very important modification that is required to be made in this Bernoulli's equation, which is conservation of energy, and what we get is actually P minus half rho v square plus h rho g is equal to constant. Please note the difference. This is plus half rho v square, whereas this is minus half rho v square. We are going to make an attempt to understand how does the Bernoulli equation get modified in case of a rotating fluid. Let us look at the top view of the cylinder. That is, a cylinder is rotating in front of me. I am looking at it from the top. So what I will see is a circular portion of liquid. So let me draw it here. This is a circular portion of a liquid which I am looking at from the top. I am going to make a differential ring. I am taking a small element here. This is the center point about which the cylinder is rotating. Let us consider this as R, and let us consider this portion as R plus VR, where the thickness is dr. As you know, the fluid is rotating, it is performing circular motion, and as the fluid is performing circular motion, there has to be a centripetal force acting towards the center. As the centripetal force is acting towards the center, the outer layer of a fluid is pushing the inner layer. So there is a net force in the inward direction. So suppose the pressure at this point is P, the pressure at this point will be more P plus dP, because the force will always be from high pressure to low pressure. If we consider a small element over here, then the force is obviously pressure into area. So if we consider a small element, again we are looking at it from the top, the force acting on this point will be P plus dP into dA, where dA is a differential area. Please note, it is not this area, but it is the area as we are looking at it from three-dimensional point of view. It is this area, it's a vertical, it's a three-dimensional element. This is the area we are talking about, and this will represent dr. This will represent dr. This is dr. So the force acting on the element, and I am looking at it from top, P plus dP into dA in this direction, and P into dA in this direction. The net force is towards the center, which is the centripetal force. So net force towards the left, as the fluid is rotating about this center, the net force towards left will be P plus dP into dA minus P into dA. This force must be equal to the centripetal force. Take a good look at it. Let me explain again. This is a three-dimensional element I am talking about. This is the front view, whereas this is the top view. If I am looking at it from this side, this is the thickness dr, which is represented here, and this is a top view. This edge is similar to this edge. So the pressure here is P plus dP dA, the pressure here is P dA. The difference of pressure acting towards the center produces the centripetal force. So now let us apply the concept of centripetal force. P dA will cancel here, and I will get dP into dA is dm, which is the mass of this element, into r into omega square, where omega is the angular velocity with which the cylinder is rotating. Now mass is volume into density. Volume will be the area of cross section dA into the thickness of the element, which is dr. Let me draw it again for you. I am drawing a pretty big scale. This is dr and this is dA. The pressure is acting like this. So it is dA into dr into dr. Let me substitute it here and let us see what we get. dP into dA is dA into rho into dr into r omega square. This is what we get. dA will cancel. If we integrate it, we will get integral dP is equal to integration of rho omega square r dr. Let us integrate between the limits P1 to P2 and R1 to R2. Suppose here the pressure is P1, here the pressure is P2, here radius is R1, and at this point radius is say R2. So we are integrating from P1 to P2 and we are integrating from R1 to R2. If we do the integral, we will get integral of dP is P. Rho and omega square are constant, they will come out of the integral. Integration of r dr is r square by 2 from R1 to R2. So if we apply the limits, it is P2 minus P1 is rho omega square by 2 R2 square minus R1 square. So that is P2 minus P1 is rho by 2 R2 square omega square minus R1 square omega square. We know V is R omega, so R into omega will be V. So the final equation will be P2 minus P1 is rho by 2 into V2 square minus V1 square. Now see carefully, This is P2 minus P1 is half rho V2 square minus half rho V1 square. If I rearrange these terms, I will get P2 minus half rho V2 square equal to P1 minus half rho V1 square. We are not considering the height element here. It is just to make you understand that it is a negative sign which will come in the Bernoulli equation. So in general we can say P minus half rho V square is constant, and if we take the height term, it is P minus half rho V square plus H rho G is equal to constant. So this is the Bernoulli's equation in the modified form, which must be applied to a rotating fluid and not with P plus half rho V square. Now let us apply this equation to our height of vortex problem. We will use this equation to find the height of the vortex which is formed due to rotating liquid. Let me redraw on a large scale. This equation is like this. It is rotating about this axis. Let me take this point as 1 and let me take this point as, this is the datum and this is the height h. Please note that point 1 and point 2 are both open to the atmosphere. It is just under the atmosphere. So pressure at P1 and pressure at P2 are both atmospheric pressures. Here the velocity is 0 because the point is on the axis. Obviously if you apply the equation V equal to R omega, there is no R, so V is 0. At this particular point, the velocity, since this is R, is given by R omega. So let us apply P minus half rho V square plus H rho G is equal to constant. So P1 minus half rho V1 square, H rho G is 0, height is 0 here, but let me write it here, plus H1 rho G is equal to P2 minus half rho V2 square plus H2 rho G. Now let us see, P1 is P atmospheric, V1 is 0, H1 is also 0. So what we get is all the 0 terms. P2 is also atmospheric, minus half rho V2 square is V, which is R omega, plus H2 we have taken as H plus H rho G. See, P0 will cancel, the minus sign will come on this side, and what we will get is H rho G is half rho R square omega square. You can write R omega as V, and you will get H rho G as half rho V square. Rho will cancel, and you will get the regular equation. H is V square upon rho G. Please understand the mechanics of a vortex. Pressure here is atmospheric. As we go away from the point inside here, the pressure goes on increasing, and here the pressure is maximum. As we go away, pressure goes on increasing. Please note, as velocity increases, pressure also increases. Here the pressure is also 0, velocity is also 0, whereas here the pressure is maximum, the velocity is also maximum. But we have not applied Bernoulli's principle here. We applied it between points 1 and point 2, but we must understand pressure here is not H rho G. The pressure here is atmospheric. Pressure at point 2 is also atmospheric. If you want to apply Bernoulli's principle, you can apply it between points 2 and 3, and you will still get the same results. But that is not required here. We can simply say apply the Bernoulli's equation between 1 and 2, and let me remind you, it is not exactly a Bernoulli's equation. It is a modified Bernoulli's equation with a negative sign. that gives us this formula. Thank you very much.